Hi friends, welcome back to the channel. Today we will be addressing the question how to characterize a random signal. Because even though the signal is random, we need to quantify it. Unless we quantify it, it becomes really difficult for us to quantify the response of the system against this particular input. So, quantifying a particular phenomena is very important step in understanding the whole phenomena. So, two parameters that are widely used is standard deviation and spectral density. Standard deviation will tell you about the intensity of the signal, while spectral density will tell you how the energy is distributed with respect to frequency. We will try to bring or build a lot of intuition around these two parameters in this video. So as shown in the graph before, a random wave never develops a repeatable pattern. It has no period, and amplitude at any point in the future is not predictable. But even then we need to quantify it. So here the theory of probability comes into picture. See, we let us for the time being keep aside the idea of predicting the instantaneous amplitude of a random signal, but rather concern ourselves with determining the probabilities of the signal occurring within certain bounds. Yes, we are talking about probability theories. So, as shown over here, this is the random signal. Now, what we are trying to do over here is that we are trying to measure the number of counts or the number of times the signal crosses a certain range of amplitude, and we are marking like this. Now, how did we get this point? We will take a range over here and then measure the number of counts. So like this, we try to draw this particular curve. It's called probability density function. What does that physically mean? It tells us that random data develop a stable average or a stable mean value, and moreover, it clusters about that mean value in a precise and predictable way. And standard deviation quantifies that. Standard deviation is a statistical parameter which measures the way the data gather about the average. More importantly, if you have a signal whose mean is 0, then standard deviation is same as the RMS value of the signal, root mean square value of the signal. This makes our life a lot easier. Here I have shown two random signals, the red one and the green one. So the green one has a less standard deviation magnitude compared to the red one. Why? Because the scatter is more. Before we move to the next section of spectral density, I would like to tell you one more thing, that this particular distribution, it's called a Gauss distribution or normal distribution, and to much of our surprise or to much of our help, most of the physical processes follow this normal Gaussian random distribution. Let us discuss how we can quantify the spectral density of a signal. In a random signal, as we all know, there are multiple frequencies present at the same time. So, in order to quantify that, a certain portion of the signal is taken for analysis as shown over here. And what enables us to do that is a certain set of assumptions. We assume that the frequency spectrum of this sample is representative of its true behavior. I have put detailed videos on what is a stationary random process and what is an ergodic random process. So we assume that the process is ergodic. A random signal is stationary if its standard deviation and spectral density do not vary with time. And moreover, ergodic is a far more strict criterion which states that this random signal whose standard deviation and spectral density is identical to a group of other random signals as well. So if you pick a random signal, it's a good representative of the whole process. So as I explained earlier, we took a certain portion of the signal which spans across time capital T. Once you decide your T, that decides the fundamental frequency in the spectrum as well as the distance between the spectral lines. Just keep that in mind. Now I would like to briefly explain what is a spectrum or what is f of t kind of a thing. Here, let's say your signal is composed of these two discrete signals, and the f of t or the your spectrum will look something like this. You have a frequency content at 3 hertz and if you have a frequency content at 10 hertz. But in contrast, a random signal has a continuous spectrum, and any frequency band we examine, however narrow it is, it contains infinite frequencies. Let me drive this point home in an example. So here I have this normal signal, or you can call the signal which is composed of two harmonic waves, and we have the random signal. Now I'm going to filter it down using two filters. Both For both filters, the center frequency is 10 hertz, but their bandwidths are 4 hertz and 10 hertz respectively. Now let's see how the signals behave when you pass them through these filters. So as you can see over here, as my bandwidth is increasing, the harmonic waves or the normal signals, they behave proper because there is only one frequency content. But in for the random signal, the amplitudes are varying, the envelope is varying. Why? Because we are looking at an infinite number of frequencies and their phase is changing. Let us try to understand that in a little bit more detail. So as shown over here, we have a random signal here. Assume that we are filtering it to three frequency ranges here. Let's say this is 5 to 10 hertz and this is 50 to 55 hertz, and let's say this is 200 to 205 hertz. So as you can see from this curves, this is quite evident. This is the low frequency signal. Here also the amplitude is changing because we have an infinite signals whose frequency is in the range 5 to 10 hertz. Here also the envelope is changing because we have infinite frequencies or signals corresponding to infinite frequencies between 50 to 55 hertz. The same holds true here also. One thing, you can see the difference in the frequency of the signals. So corresponding to each of these signals, we can compute an RMS amplitude. So we'll get this point corresponding to this particular bandwidth, corresponding to this we'll get this point, and corresponding to this bandwidth we will get this point. Connecting this together, we will get the PSD. This is RMS amplitude divided by the bandwidth. If we consider, that will give you this y-axis value. This is what is called as a spectral density. Now logically another question arises, why we are dealing with RMS amplitude? Because we are dealing with large number of harmonic waves or signals which may or may not be in phase. RMS value is the logical quantity as RMS measurements are insensitive to phase. Moreover, if two waves are not in phase, then you cannot add their amplitude simply. This is another reason. But RMS amplitude is able to take care of signals which are out of phase as well. So this particular vertical axis, whatever I just shown you, is the spectral density, and it's a measure of the total mean square of all frequencies existing in a bandwidth of 1 hertz. So what we discussed in this particular unit was what are the parameters to characterize a random signal and what is its physical significance. Parameter 1 was the standard deviation, which characterizes the intensity or the dispersion about the mean value, and another is the spectral density, which talks about the distribution of energy. Thank you.